Hi guys, so today's going to be a talk about conditional probability. I'm going to try to give a little bit of motivation for the definition of conditional probability, and then I'll derive a few formulas, but as usual most of the examples will be saved for class. So we're going to derive a few formulas and you'll want to know them coming in, so that way you can use them or you'll be familiar whenever we start using them in class. So what we're talking about so far is we have the space omega, which is the space of all possible outcomes of some kind of experiment, whether it be a die roll or flipping a coin or whatever. I mean, there's some space of outcomes. And I'm going to draw a Venn diagram type picture here. So let's talk about two events in omega. So maybe we have an event A, where this represents the different outcomes that belong to A. It's a subset of omega. And then we have some event B, which is a subset of omega. And we're just representing this through a Venn diagram, which hopefully you guys are used to, or at least familiar enough with to know what this means. And when we put a probability on omega, remember that the probability of the entire space is 1. So we know the outcome is going to belong to this space with probability 1. And then we can compute, say, the probability of A and the probability of B and so on is just some way to measure the likelihood that the outcome is going to be in A, or the way that the likelihood is that the outcome is going to be in B. So it's just a way to measure these sets. But suppose we know that the outcome is in B. So we want to know if it's in A or not. But somebody tells you, well, we know it's in B. So an example of this might be you roll a die, or say your friend rolls a die, and they cover up the die whenever they roll it, and they tell you, oh, I got an odd. Well, before they tell you that, if they just roll a die, the probability they got a 1 is 1 out of 6. Right? It's because there's just a 1 out of 6 chance you get any number when you roll a die. But if they tell you they got an odd, that changes now. So the probability is no longer 1 out of 6 if you know they have an odd. So let's see how would the formula change whenever we go to compute this. So if we know that the probability is in B, we can basically ignore all this stuff that's not in B. Right? Forget B complement. We just care about B. So let's blow it up a little bit. This is our set B. And so now this is like the new omega. And so the measure of this thing is going to have to be 1. Right? If this is everything, if we know it's in B, and we're told that, then the probability that B occurs is 1. And how would we take the probability of B and make it 1? Well, we could just divide by probability of B. So P of B over P of B scales everything, so now then the probability of B is 1. And we want to know if A occurs or not. So here's this little piece, like that. This is the stuff that's in A. So A was this whole set, but we threw away everything except for that little sliver. Or, well, I call it a little sliver. It's really just what's in A intersects B. Right? So this whole thing is actually A intersects B from the original picture. So the probability that this happens, given that we know the only possible outcomes are in B, is going to be the probability of A intersects B. But we still have to scale it. Since we had to scale everything so that B has probability 1, we now have to scale this piece too. So we've scaled the whole space, so it's scaled by P of B. And so that's the probability of A intersects B divided by the probability of B, which is the probability of A given that we know B occurs. And so this is a little bit of special notation here. So usually the probability is how likely does this event occur? How likely is this event to occur? Or what's the probability it occurs? Here, what's the probability that A occurs? Then the vertical line means, well, to the left of the vertical line are the events we're computing the probability of. But to the right of the vertical line are the events we know. So I know B has happened. Now what's the probability A has happened knowing that B has happened? So let's write the probability of B given A. Or sorry, the probability of A given B. So we know B happens, we're told that. So given that information, what's the probability that A was still an outcome? So that's the formula, and that's a bit of the intuition behind conditional probabilities. So our conditional probability formula is the probability of A given B is the probability that A occurred in the space, so we only look at the things that are also in B, so A and B, divided by the probability of B, our scaling, so that, that B has probability 1. So that's our formula. Now from this we can derive other formulas. So in the examples we'll see when sometimes it's useful to use these other formulas. One might be the probability that A and B occurs. Well, this is equal to the probability that A intersects B happens times the probability of B divided by the probability of B. So notice all I did was multiply and divide by the probability of B, and that just cancels off. So really I didn't change anything. These two must be equal, right? Because this just cancels. And now let's write it a little bit differently. So this is probability of A intersect B over probability of B times probability of B. And the probability of A intersect B divided by the probability of B is P of A given B. So we can really write this as the probability of A given B times the probability of B. So that little bit of algebraic manipulation gives us a new identity. So given this formula, and this is our definition of probability of A given B, this one's a definition. And then we derived the probability of A intersect B is the probability of A given B times the probability of B. And here's a place where we can use induction again. So this works for 2 events, but we can actually do it for more than 2 events. So let's say we have the probability of A1 intersect A2 intersect and so on down to AN. Well, we could treat this one as like the A and treat all of this stuff as like our B. So this is actually equal to the probability of A1 given that A2 occurs and A3 occurs, and so on down to AN. So we know that all these occur, but then we just multiply that times the probability that, let me go down to the next line, so this is multiplied times the probability that A2 intersect A3 intersect so on down to AN. But now we still have an intersection of events, so we treat A2 as like our new A, and A3 through AN is like our B. So substituting in again, we didn't do anything to this first piece. So the first piece is just P of A1 given A2 intersects down to AN, and then we multiply times P of A2 given A3 down to AN, and then we multiply times the probability of A3 intersects down to AN. And so this will just continue, dot, 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 until we have the probability of A1 given A2 intersects down to AN times the probability of A2 given, then starting with A3 down to AN. And we keep multiplying these things out until we have the probability of AN minus 1 given AN, and finally just the probability of AN. So we can change the whole sequence of intersections into conditional probabilities. Okay. So now let's talk about another formula to just compute the probability of an event. Maybe we want to compute the probability of an event A. But perhaps it's a lot easier to compute this probability if we know something about another event. So maybe if we know that B happened, it's real easy to compute A, and if we know that B didn't happen, it's easy to compute A. But maybe if we don't know anything about B, it's much harder to compute A. So the idea here is if telling us something about B makes it a lot easier to compute it, then we can break it up this way. So this is, well, now we want to use a little bit of set theory. So let's go back to our Venn diagram. If this is A and this is B, this piece of A here, this is the stuff that's in A but not in B. In other words, it's an A and B complement. And this piece here, this is the stuff that's in A and in B. So this is A intersect B. And so what we have is that A as a set is equal to A intersect B complement taken together with, or unioned with, A intersect B. So everything has to be in A and not in B, or it can be in A and in B. But if it's already in A, it's going to have to be in B or not in B. So we just break it up to the stuff of A that's not in B and the stuff in A that is in B. Also, nothing can be in A and not in B, and in A and in B. I mean, these are all ands, but you can't be in B and not in B. So this is the empty set, it's disjoint. And so now let's use this. So the probability of A is equal to the probability of A intersect B complement union A intersect B. So all we did was made a long substitution for A, because these two things are really equal. But because these are disjoint, by rules of probability, this union can turn into a sum. So really this is the probability of A intersect B complement plus the probability of A intersect B. And now then we're going to use this product rule again. So the probability of the intersection of two things can turn into a conditional. So this is the probability of A given B complement times the probability of B complement plus the probability of A given B times the probability of B. And so that gives us a new formula. So here's another formula. The probability of A is equal to the probability of A given that B doesn't happen times the probability that B doesn't happen plus the probability of A given that B does happen times the probability that B does happen. So that's another handy formula to know that might give us some shortcuts that we'll use in class for certain examples. Okay, and last one. So this is called Bayes' rule. So here the idea is, suppose that we want to compute the probability of A given B. But what we know is we actually know stuff about the probability of B given A. So we can write this as the probability of A intersect B over the probability of B. That's our first formula. It's just that this equals this. Now then the probability of A intersect B, we can use this formula, but let's interchange the roles. So the probability of A intersect B is the probability of B given A times the probability of A. And then for the bottom, we're going to use this formula, except for, again, we switch the roles of A and B. So instead of probability of A, we're doing it with B. So it's going to be the probability of B given A complement times the probability of A complement plus the probability of B given A times the probability of A. So look what we've done is we've switched all the conditions. We wanted to know something about A if we're given B, and we switched it into a formula that we can use the probabilities of B given something about A. Alright, so this formula and these three up here are the ones you're going to want to be familiar with for the next lecture or two. And we'll go through some examples. Alright, well, God bless you guys. See you soon.